Section 10.2 is all about sequences. Before we get into the meat of it, though, I want to remind everybody about a few things. So first of all, we want to review L'Hopital's rule. Now, L'Hopital's rule is really recent, so we shouldn't need to spend too much time with this. But it's just a reminder that if you have a limit as x goes to a of f of x over g of x, that's equal to the limit as x goes to a of f prime of x over g prime of x, provided that the indeterminate form f of x over g of x is in 0 over 0 or infinity over infinity form. Remember, there are other indeterminate forms, but those require manipulation in order to be able to work with them. Right? Those 5 indeterminate forms. All right, so just a reminder, let's find the limit as x goes to infinity of the natural log of x over x. Now the form on this is infinity over infinity because the natural log of infinity is infinity, and obviously x is infinity, right? So according to L'Hopital's rule, I can take the derivative of both of those and take the limit of that. Now remember, this isn't actually equals. That's why we pull the L apostrophe HOP or L apostrophe H above the equal sign. They're equivalent. They're not strictly exactly equal. So this would be 1 divided by x over, because the derivative of natural log of x is 1 over x, over 1, because the derivative of x is 1. And so that means that I'm taking the limit as x goes to infinity of 1 over x, and that is 0. You're not technically substituting in infinity. I mean, we kind of write it like that, but it's really more thinking about it. Which leads me to a couple more notes. Just a little few reminders. That remember that the limit as n goes to infinity of k over n, where k is a constant, is 0. Actually, let me put it there, is 0. Right? That's not indeterminate, right? So if k is some constant, and you take constant and you divide it by infinity, you will get 0. Number 1. Number 2, if I take the limit as n goes to 0 of k over n, that's either positive infinity, negative infinity, or sometimes both, depending on direction. Right? Sometimes it's positive infinity if you come from the positive side, but negative infinity from the negative side, and vice versa. Right? It's still not indeterminate, right? So we know what these things are. Similarly, we know what infinity plus infinity is infinity. Negative infinity minus more infinity is negative infinity. 0 to the infinity power is 0. And similarly, 0 to the negative infinity power is also 0. So these forms we actually know. They are determined. They're not indeterminate, in other words. So we know what they are. You don't use L'Hopital's rule for them. We know how they work. We learned them in Calc 1. It's one of the important things that your instructor would have stressed to you in the limit chapter. All right, now where am I going with that? We all know this. We've done this recently. Well, there was a rule in Calc 1 that your instructors usually teach you to kind of get you through Calc 1, but you don't really know the reasons why it's working. So this is actually stripped right from my notes in Calc 1. These are the guidelines for finding limits at infinity, right? Limits at infinity mean you're heading towards infinity of some function, right? Well, we learned that if the degree of the numerator is less than the degree of the denominator, that's case 1, right? So if your degree of your numerator is less than your degree of your denominator, then we learn that the limit will be 0. If the degree of the numerator is equal to the degree of the denominator, which I'll make case 2 right here, if they're equal in degree, then the limit of the rational function is the ratio of the leading coefficients. And then third, if the degree of the numerator is greater than the degree of the denominator, then it's either positive or negative infinity. All right, now those were guidelines. They were guidelines that we learned and worked with and all of that. But they're because of and can be found with L'Hopital's rule. So we kind of fake our way through it in Calc 1, but the reason they are happening is because of L'Hopital's rule, which not every Calc 1 teaches. One more thing really quickly. What is a rational function? I just want to make sure I define that, because you'll notice that it says rational, rational, rational. So a rational function is when you have a polynomial divided by a polynomial. That's a rational function, right? So you have x to some power with a lot of other stuff, and then x to another power, right? That would be a rational function. Now, these rules only work for limits at infinity. It doesn't work for other pieces. So it has to be that you're working towards infinity. So it needs to be the limit as n goes to infinity. That's the part that matters. If it's other things, then we can't use this. And it only works with rational functions. It has to be a polynomial. I wrote it up above, but I'll say it again, divided by a polynomial. Now, we're going to allow it to kind of finagle your way out of this. So we'll let you use these guidelines, right? These guidelines come from things, but we can prove them with L'Hopital's rule. So let's look at our candidates here. So if I look at this particular one right here, I'm taking the limit as x goes to infinity. There's that infinity. X cubed plus 9x minus 4 over 6 minus 4x cubed plus 7x squared. So this is a case 2, right? The degree of the numerator is equal to 3, and the degree of the denominator is equal to 3, because degree is the highest power out there, which is 3 in both of these cases. Therefore, according to case 2 logic, I can take a ratio of the leading coefficient right here and right here. And I can say that the limit as x goes to infinity of that function is positive 1. We don't write it because we're lazy, but there's a number there. It's 1. If it was 0, you wouldn't see anything at all, right? There would be no x cubed. So it's 1 over negative 4. And you're done. But of course, the reason this works is because of L'Hopital's rule. If I just take derivative after derivative after derivative, eventually it'll break down to a ratio where the top number will be a fourth of the bottom number, and the bottom number will be negative. All right, so that was case 2. Now, what about this one over here? It has degree 3 on the top, degree 5 on the bottom. Easiest case there is, that would be case 1. So this is case 1. Right, the degree of the numerator is 3. The degree of the denominator is 5. Therefore, this is 0. And we love it when those problems are that easy. Isn't that great? All right, now what about C? Well, C is a little bit more work because we have the degree of the numerator is greater than the degree of the denominator. So we can mess around with this a little bit, or we can use L'Hopital's rule. So this is definitely a case 3 because the degree of the numerator is larger than the degree of the denominator. The degree of the numerator is 2. The degree of the denominator is 1. All right, well, according to L'Hopital's rule, which I'll do right here, I'll put a little L'Hopital on this. It's the limit as x goes to infinity of 4x minus 4 over the derivative of the denominator, which is 1. So if I let x go to infinity, that's 4 times infinity minus 4, which is infinity. Now, what about letter D? It seems very similar, right? And it is. Degree of the numerator and degree of the denominator are the same as they were in letter D. However, according to L'Hopital's rule, it would be the limit as x goes to infinity of negative 4x minus 4 over 1. So that would make it the negative 4 times infinity minus 4, which would be negative infinity. Like that. And of course, the degree of the numerator and denominator works for both of these because they're basically the same problem. Now, I didn't bother to show all of the L'Hopital's rules that get us through A and B because, quite frankly, it gets tedious after a while. So we can use these guidelines, but recognize that they come from L'Hopital's rule. And if worse comes to worse and you're forced to show it by hand, you could show it by hand. You could take derivative after derivative after derivative to get to these answers. In this case, you can also take derivatives to get to them. It was a little bit easier to figure out whether it would be positive or whether it would be negative by putting them in after you've taken a derivative. But if you wanted to, you could have logicked your way through this one to begin with, right? If you have infinity squared, that's infinitely larger than infinity on the bottom. So therefore, the infinity on the top will win, things like that. So you can sort of logic your way through it like we do in Calc 1, but now we have L'Hopital's rule at our disposal. Nevertheless, we will use these guidelines on this page throughout the next couple chapters. So just be prepared to refer back to them on the regular basis because we'll use them a lot without bothering to show the L'Hopital's rule. But recognize that L'Hopital's rule is where they come from. So L'Hopital's rule is how you could prove them or do them by hand if you had to.